A very good morning to one and all. I welcome you all for session number 31. In this session, we will see yet another application of Lagrangian equation to Atwood's machine. In the previous class, we have applied Lagrangian equation of a motion for a simple pendulum, where Lagrangian term was found to be of ml square theta dot square minus mgl into 1 minus cos theta. And using Lagrangian equation, we arrived theta double dot plus g by l sine theta, which is the equation of motion for a simple pendulum. However, if the amplitude is very small, sine theta can be approximately equal to theta. So then the equation becomes theta double dot plus g by l theta is the equation of motion for a simple pendulum. The main objective of this session is how to derive kinetic energy and potential energy for a constrained motion, and how to apply Lagrangian equation of a motion to Atwood's machine. By the end of this session, you will come to know how Lagrangian equations are used to arrive the equation of motion for Atwood's machine. Now let's understand what do you mean by Atwood's machine. It is a system of two masses connected by an inextensible string passing over a small smooth pulley. This setup is known as Atwood's machine, and it is an example of conservative system with holonomic constraint. It is two bodies of mass m1, m2 are connected by an inextensible length of wire L and pass through a small smooth pulley. Now let us consider two bodies of mass m1 and m2 connected with a length of wire L passing through a smooth pulley. With reference to pulley, let us consider x be the distance of mass m1. So L minus x will be the distance of mass m2 with respect to pulley. Now for this setup, I need to know its potential energy as well as kinetic energy. So we see that it is having only one coordinate as x. So let v1 is equal to x dot be the velocity of m1 mass, and v2 is equal to minus x dot be the velocity of mass m2. Then the kinetic energy of the system, the two masses, is T is equal to of m1 plus m2 into x dot square. Now this is the kinetic energy. Now I need to know potential energy. Potential energy, there are two bodies m1 and m2, which means I have two potentials, one with respect to m1 and one with respect to m2. So therefore potential energy V is equal to minus mg1x minus m2 into L minus x. Now I have found the kinetic energy and potential energy for the system. Now we know that the Lagrangian term is given by L is equal to T minus V. Substituting the values of T and V, we arrive L is equal to of m1 plus m2 x dot square plus m1gx plus m2g of L minus x. Now to apply Lagrangian equation, I need to differentiate L term with respect to x dot and L term with respect to x. So on differentiation dou L by dou x dot, we arrive m1 plus m2 x dot. So similarly, dou L by dou x will be equal to m1 minus m2. Substituting in the Lagrangian equation, that is d by dt of dou L by dou x dot minus dou L by dou x will be equal to m1 plus m2 x double dot on differentiation minus m1 minus m2 is equal to 0. On rearranging these terms, so x double dot will be equal to m1 minus m2 into g divided by m1 plus m2. This is the required equation of motion for Atwood's machine. Now, based upon their masses, let's have two cases. So, case number 1. If the mass m1 is greater than m2, then definitely m1 descends with constant acceleration. In case 2, if m1 is less than m2, then mass m2 ascends with constant acceleration. If both the masses are equal, so then x double dot is equal to 0. Then we are moving with a constant velocity. Note that tension in the rope, the force of a constraint is not seen anywhere in Lagrangian equation. This is the beauty. Now you see that we have applied Lagrangian equation to arrive equation of motion for Atwood's machine. So now let's have a small MCQ session. Question number 1. Atwood's machine is an example of dash constant. Here we have seen it is an example for holonomic constraint. Question number 2. The coordinate chosen as generalized coordinate in Atwood's machine is, we have chosen x to be the coordinates. So answer is option C. Question number 3. Kinetic energy equation in Atwood's machine is of m1 plus m2 x dot square. So the option is answer A. Question number 4. The potential energy in Atwood's machine is minus m1gx minus m2gl minus 6. So the option is C. Question number 5. Lagrangian equation of Atwood machine is, it is the sum of, difference of potential and, kinetic energy and potential, that is of m1 plus m2 x dot square plus m1 gx plus m2g of L minus 6. So the option is C. Question number 6. Dou L by dou x is, we have seen it is m1 minus m2 of g. Question number 7. Lagrangian equation for Atwood's machine is, so that is m1 minus m2 into g divided by m1 plus m2. So the option is D. Question number 8. In Atwood's machine, condition for mass m2 to ascend is, if it is m2 should move upwards, then mass m1 should be greater than m2. So m1 is less than m2. In Atwood's machine, condition for mass m2 to descend with a constant acceleration is m1 should be greater than m2. So the option is A. Question number 10. In Atwood's mission, potential energy is obtained with reference to, all these are with respect to pulley. That is with respect to pulley, option D. So in this session, we have seen yet another application of Lagrangian equation for Atwood's mission. Thank you all. Hope you enjoyed this session.